Okay, another experiment. So this time, here's our experimental setup. We're colliding a 1 kilogram ball on the left going 2 meters a second with one on the right going 1 meter a second. And this is pretty much identical to the last setup for the previous video. But this time, the balls aren't billiard balls. They're not pool balls. They're made of, say, Play-Doh or clay or something that is going to make them stick together when they deform and stay deformed. So we run this experiment, we see them collide, and they go floomp, and they kind of deform and stick together into one big 2 kilogram clump, and we measure that clump to be going 0.5 meters per second. What is the initial momentum of this two-ball system and the final momentum of this two-ball system, and are they the same before and after? Because if they are, we can conclude that momentum is conserved in collisions. This is about the opposite side of the spectrum as the last collision. The last collision was almost completely elastic, about as close as you can actually get, and this one is completely inelastic. Because these balls didn't bounce at all off each other. They stuck and they remain connected and touching. Alright, so let's add up the momentum of the two-ball system before the collision. There we go, it's actually exactly the same as the last example. And that was the initial momentum before collision. The final momentum of our two-ball system, which is now just one big clumpy ball, final momentum would be, well, let's just combine this, pretend those two balls is now one object. So it would just be the final mass of that one object times its velocity that it has after the collision, which is 2 kilograms is the m, and the v is the 0.5, and 2 times 0.5 is 1. So again, we have momentum conserved in the collision. So we've seen that momentum is conserved on both ends of the spectrum of elasticity of collisions. So I'm hoping that since we did these little experiments, everybody will definitely remember that momentum is always conserved in a collision. That is the momentum of the entire system of objects that are colliding. You can't just look at one of these balls and say, well, its momentum is going to be conserved after it hits this other ball. We have to incorporate both balls into our system. Alright, so momentum is always conserved. Now let's look at kinetic energy. Is kinetic energy nearly conserved in this inelastic collision? Let's find the initial kinetic energy of the two-ball system before the collision. And this is exactly what we did last time. We found that it had 2.5 joules of energy. The entire two-ball system did before those balls collided, and after, well, again, we can kind of model these two balls as being one clump now. So we just have 1/2 mv squared, and the m here for this two-ball clump is the sum of both of the ball's masses, and the final velocity was 0.5, and we have to square that. And that ends up being a very low number of joules, because the speed of both the balls has been dramatically reduced. A lot of motion has been removed in this collision, and because kinetic energy is proportional to the square of the velocity, that has a profound impact on the kinetic energy. So we end up losing most of the 2.5. We actually lose 2.25 joules. And so to conclude, we find that kinetic energy is not conserved in an inelastic collision.